Well, okay, so it's almost 4 minutes past 2, so let's open our Sano computational medicine seminar. And today, after the break we had last Monday, a break with Markowicz accounting. Today we come back to presentations of research of Sano PhD students. And today as a speaker is Michał Grzeszczyk. Michał is a member of Health Informatics team. Before joining Sano, he was graduated from Warsaw University of Technology and Technical University of Berlin. And he was also spent some time as a visiting researcher at the University of West Scotland, as well as Institute of Biocybernetics and Biomedical Engineering, which is part of Polish Academy of Sciences. And now he is pursuing for his PhD at, as I already said, Health Informatics team, which is led by, already probably noticed after previous PhD students' presentations, which is led by Przemek Korzeniowski. And I think that it will be good if Przemek will introduce Michał and his research area. Przemków, screen is yours.
Yes, so Michał's specific research is on multimodal data fusion and with the particular focus on combining imaging and tabular data in medicine. This work led to several publications and top-tier conferences, specifically MICAI. And Michał last year received award for Best MICAI Reviewers, and his latest submission on TabMixer got early acceptance, which means that it was top 11% of best papers submitted to MICAI, which, as far as I remember, is nearly reaching the number of submissions 3,000. So it's 25% increase from last year. So it's getting extremely challenging. So well done, Michał. Congratulations, and looking forward to your seminar. Thank you.
As usual, if you had an urgent question during Michał's presentation, please put it on chat or on questions and answers, and I will try to stop Michał, and Michał will try to answer your question. But the most important part of the seminar will be, from the point of view of questions, will be discussion after Michał's talk. So now, Michał, screen is yours.
Thank you, Marian. I hope you can all see my screen and hear me. So hello, everyone. Good morning. My name is Michał Grzeszczyk, and as was already mentioned, I am a PhD student at Sano Center for Computational Medicine in Health Informatics Research Group. Today, I would like to take you on a short journey on how my research transitioned from solely medical image processing towards multimodal learning and fusion of imaging and clinical data. And my research is mainly supervised by Professor Arkadiusz Sitek. So let's start with the beginning. As you probably know, many clinical procedures involve collecting data samples in the form of imaging and tabular data. Those could be cardiac MRIs combined with blood test results, or fetal ultrasound combined with fetal biometry or mother's medical history. And we know that clinicians are looking at all the information that is available for them to make the diagnostic decisions or decisions regarding further treatments. But when it comes to deep learning and machine learning approaches, many of the proposed solutions and algorithms focus on unimodal-based predictions, on unimodal-based training. And this led to our investigation regarding whether we could efficiently utilize both modalities. Maybe we could find a way to efficiently get the idea, the information from tabular data and imaging data at the same time in order to get improved performance of our models. From the investigation of this problem, we reached a couple of research questions. A couple of them were technical, and as you know, we are working in the computational medicine area. Therefore, we also had clinical questions from our collaborators from Medical University of Warsaw and the University of Sheffield. But let's start with technical questions. So a couple of years ago, the attention mechanism became quite popular, and many modules based on attention were being developed to improve predictive capabilities of deep learning models. And we decided to check whether it would be possible to use tabular data to condition the process of attention maps generation in order to further improve the capabilities of deep learning models. Second of all, when it comes to tabular data and deep learning, multi-layer perceptrons, MLPs, are the go-to standard, or were, over the last years, the go-to standard for tabular data processing. And as well, a couple of years ago, there was the idea of creating MLP mixer architectures for image processing for vision tasks. And we thought that maybe we could combine the idea of using MLPs for tabular data processing with the idea of using MLPs for imaging data to mix the information from both tabular and imaging modalities. And finally, when it comes to clinical questions, we were working on two tasks. First of all, we had the fetal birth weight prediction, which is being conducted from fetal biometry, but has quite huge error. Therefore, we would like to decrease the error of fetal birth weight prediction. And second of all, pulmonary hypertension requires invasive diagnostic procedures. So we would like to create some non-invasive alternative based on artificial intelligence, and we are investigating it in my PhD project. Let's start with fetal birth weight prediction. So when it comes to our weight, which is one of the most and simplest metrics when it comes to the analysis of our health and state of our health, we can easily measure our body mass by using weight and then deciding whether the mass is too high, too low, or maybe it's perfect. But when it comes to fetus, which is still in mother's womb, the idea of weighing it is slightly more difficult because we can't do it directly. Therefore, clinicians are using many indirect heuristics, some mathematical formulas to estimate the fetal weight. And how it is being conducted? The idea is that for example, during the ultrasound examination, 24 hours before the delivery, doctors want to decide whether the delivery should be conducted through natural or cesarean delivery. And therefore, they are collecting ultrasound videos of 3 body parts, which is head, abdomen, and femur. And then from those frames, from those videos, they are extracting standard planes from which they can measure fetal biometry. It could be head circumference, head diameter, abdominal circumference, or femur length. And then the final step is to use a simple mathematical formula to estimate the fetal weight. The problem with this formula is due to the fact that it's very simple, it's relatively easy to use, but the problem is that the error of the fetal weight estimation prediction might be quite high, up to 15%. Therefore, we would like to decrease this error, and we asked ourselves a question whether we could do it better, whether we could decrease the prediction error made by clinicians. And during my initial research at Sano, we've been collaborating with Szymon Płotka on the fetal birth weight estimation task, and we have decided to check whether we could directly from ultrasound videos predict the fetal weight. And that was the results of this research were published at MIGCAI 2022. So the data set that we had was consisting of more than 200 2D fetal ultrasound videos from more than 70 patients, which were those ultrasound videos were performed 1 day prior to the delivery. And of course, our prediction target was the birth weight of the fetus obtained just post the delivery. So we wanted to analyze the 3 views acquired during ultrasound examination. But the problem was that we had a couple of constraints. So we had memory limitations, and the ultrasound videos contain many noisy frames. And it turns out that, for example, if we have 100 or 200 frames in the video, some of them contain only noise without any information. So due to this fact and the memory constraints that we have decided to follow some kind of ensemble of predictions. So we splitted ultrasound videos into 16 frame segments, and then we averaged the predictions of all the videos, but of all these segments. But the question is, what possibilities did we have? What models we could try for the video processing, for spatiotemporal analysis? So of course, there are multiple of existing methods, but I wanted to mention the most important ones when it comes to our research. So first of all, from 2D ResNets, from 2D convolutional neural networks, of course, the 3D representatives appeared, and there were multiple variants of 3D ResNets. For example, 3D ResNets could be created from 3D and 2D convolutions, or only 3D convolutions, or 2+1D convolutions. But also at the time, there was quite huge boom, and still is, regarding transformer-based architectures, and especially vision transformers. So after introducing vision transformers, of course, video vision transformers appeared. But the issue with this type of architecture is that they require huge amounts of data. And as you could see earlier, our data set was quite low scale. So we have decided to follow some kind of hybrid approach where we could use a combination of quite efficient convolutional neural networks with transformer-based architectures. And we based our solution on the bottleneck transformer, in which the bottleneck convolution was replaced with multi-head self-attention layer for finer feature refinement at the end of the network. And we proposed our architecture, which was called BabyNet, which was supposed for spatiotemporal ultrasound video scans analysis, in which we introduced our residual transformer module. And this RTM module consisted of a convolution layer followed by multi-head self-attention for finer refinement of the extracted features just before the regression layers at the end of the network. And here you can see another figure of how we integrated our multi-head self-attention layer with 5-stage convolutional 3D ResNet. And of course, the output of the model was the predicted birth weight from the 16 frame segments of fetal ultrasound videos. And when we take a look at the results, there is quite interesting thing showing for us. First of all, when it comes to the comparison between imaging models, our BabyNet architecture was achieving the best results. So it was a good indication for us that our hybrid approach was giving a performance boost. But the problem was that the methods conducted by clinicians was, first of all, achieving lower error, lower prediction error. And second of all, it was much simpler. Therefore, it wouldn't be advantage. There wouldn't be any advantage of using our solution. But the interesting thing showed up when we have decided to average the prediction of our BabyNet and the prediction of clinicians. It turned out that the ensemble of those predictions returned the lowest error, giving us some kind of the indication that maybe there is something important in fetal biometry, but also something important in fetal ultrasound videos that fetal biometry might be missing. Therefore, we have decided to work further on those approaches, but now we have decided to improve our architecture, our BabyNet architecture, to create BabyNet++ model, in which we would combine multimodal data acquired less than 24 hours before delivery. And the results of this study were published last year in Computers in Biology and Medicine journal. Here in this study, we had slightly bigger data set because we had nearly 600 2D fetal ultrasound videos. And additionally to those videos, we were analyzing tabular data. So we were having 6 numerical features, the one that I presented earlier, like abdominal circumference or head circumference, but we also had the gestational age and mother's age. And similarly, as earlier, the birth weight of the fetus obtained post-delivery was used as the prediction target. So we started investigating what are the possible methods, algorithms that we could use when it comes to multimodal learning, especially in multimodal learning combined with tabular data. So, of course, the first idea that came to your mind and came to our minds was the simple concatenation. In this kind of approaches, we just take one deep learning model, which is used for feature extraction. It could be, for example, convolutional neural network. And then after extracting imaging features from the image video, we can concatenate one D vector, which is global average pulled from imaging feature vectors. We can concatenate it with tabular features. And of course, this might improve our performance, but the problem is that the interaction between those features is quite limited. The tabular features are only used after global average pooling, so there is no spatial information anymore, and it is happening at the end of the network. Even if we take some different kind of concatenation approaches like probability fusion, feature fusion, or learned feature fusion, the interaction is quite limited. So, of course, there appeared a couple of more advanced methods for the integration of imaging and tabular data. For example, on the left-hand side, you can see the interactive model, which is based on 2 branches, the clinical data branch, which processes tabular data, and imaging data branch. And the idea is quite straightforward because here the tabular embeddings are being channel-wise multiplied by imaging features. It's still quite simple approach, but gave some improvements over concatenation. On the right-hand side, you can see slightly different methods which are based on affine transformations of imaging feature maps. So feature maps are being shifted and scaled based on the alpha and beta vectors or gamma and beta vectors when it comes to film. And the scale is being created via simple multiplication, and shifting is created via simple summation. The difference between film and DAFT is just the way how the alpha and beta vectors are being computed, because in DAFT, imaging feature maps and tabular data is used for for the computing of alpha and beta. And when it comes to film, only tabular data is used for those affine transformation vectors. And we have decided to follow the affine transformation approaches and created BabyNet++ architecture, in which we also followed our 16 frames averaging segments approach. And we have created BabyNet++ architecture. In this architecture, we have added DAFT module, which I am going to explain in more details shortly, but we have extended our residual transformer module in order to take not only imaging feature maps and to process them by simple 3D convolutions and then multi-head self-attention layer, but we also added DAFT for the integration of tabular data. And here you can see, again, the drawing, the figure of how BabyNet++ looks like with the integrated DAFT module in the final convolutional stage of the ResNet architecture. When it comes to DAFT, you could see the exemplary drawing a couple of slides earlier, but here again, let's repeat it for a moment. We are just computing alpha and beta vectors, so the solution is quite simple. The positive thing is that it's not overfitting that much, because we are learning only a couple of alpha and beta values for every channel that is there. But the idea is that we are global average pulling feature maps, we are concatenating it with tabular data, passing through fully connected layers, which return the specific amount of alpha and beta values that is required by a channel, by the number of channels in the feature maps that are available for us. And when we take a look at the results that we achieved in this research, we could see some positive thing here. First of all, our methods outperformed both imaging-based methods, tabular-based methods, the combination of imaging and tabular-based methods, but we managed to exceed the performance of clinicians, which gave us the idea that the overhead of training, deploying the model might give us some kind of advantage when using deep learning-based approaches. And second of all, we also investigated which fetal body part was giving the best results, which fetal body part was giving us the highest information gain, the lowest prediction error. And as expected, it turned out that the abdominal plane the inference made on abdominal plane was giving us the lowest error. And it was quite expected due to the fact that abdominal plane shows us many organs as well as fat tissue. We can see the beating heart sometimes in the videos of abdominal plane view. Therefore, it contains most often the highest information. And finally, what was quite important for us is that thanks to not only utilizing the tabular data, but also imaging data, our solution was quite stable and quite robust when it comes to intra and inter-observer variabilities of all fetal biometry measurements. You can see that if we alter the measurements acquired by clinicians, the performance loss was much lower for our method in comparison to others. But we haven't stopped on this approach, because we used the method that was proposed by other researchers, and we thought of going slightly farther with our research and with developing new approaches for integrating tabular data within vision models, because the ones that I have shown you were quite simple, and maybe there was something in the algorithms, in the methods that were being developed, presented by other authors. Maybe there was something that we could work on to integrate tabular data within vision networks and achieve even better results. And that led us to our MidKai 2023 publication, in which we presented Tab Attention module, which enables learning attention conditionally on tabular data. In this paper, we focused only on the analysis of the abdominal plane view, because we've seen the best results when it comes to abdominal plane view analysis, and we could train our models faster and see which of our developed solutions were giving us the best results. And here again, we were using 6 numerical features from fetal biometry, gestational age, and mother's age. And again, the birth weight was used as the prediction target. And at this point, we had decided about our attention module, our base for attention module that we would like to work on. And one of the most popular attention modules that are there, you might have heard about it, is convolutional block attention module. And the idea of this module is very, very simple. So we have input feature maps, which have channels, channel dimension, height and width. And then we compute 2 types of attention maps, attention vectors. First of all, we have channel attention module, which allows us to compute the channel attention vector. And then this vector is being multiplied by the input feature maps. Sequentially, we are then computing spatial attention map, which is a 2D attention map. And we are again multiplying by the output from the previous attention module. How those attention vectors or maps are being computed. Here, again, the idea is quite straightforward. So when it comes to channel attention module, we are average pooling and max pooling over all the other dimensions other than channel dimension. And when it comes to spatial attention module, we are max and average pooling over channel dimension in this case. In both cases, we are receiving 2 vectors or 2 maps, max and average pooling vectors, which give us more or less the most important information, the average information and the maximum information that is there in the feature maps, which we can later process via dimension-specific layers. So for example, we can have multi-layer perceptrons when it comes to channel attention, or we can have convolutional layers when it comes to spatial attention. So the idea is quite straightforward, and we wanted to build on top of this idea and develop our own solution. So here you can see slightly different drawing of a convolutional block attention module, but here, instead of 2D image processing, we were processing the temporal information. We were processing videos. Therefore, we had to focus not only on channel attention and spatial attention, but we also had to add another component of temporal attention, especially in case if we have videos like ultrasound videos in which some of the information is unnecessary at specific frames because they contain noise, and on the other hand, some frames are quite important because they visualize fetal body parts. And finally, my presentation is about the integration of tabular data. So in addition to the temporal feature maps, those attention modules were supposed to get also the tabular data as an additional input. And here you can see simple mathematical formulas on how the information was being processed by the tab attention module. So how did we integrate the tabular information within those attention module? Again, we followed the intuitive approach created by the authors of convolutional block attention module. But apart from average pooling vectors and max pooling vectors, we also wanted to add the information from tabular data. Therefore, we have decided to embed tabular data into the vector or 2D map the same size as the pooled vectors or maps from the feature maps. In this way, we could pass those tabular embedding vectors through the dimension-specific layers and combine the tabular information within image information to create attention maps or vectors for the refinement of future maps in vision networks. We followed the same approach in spatial attention module. Here we have a little bit of a limitation when it comes to our approach, because we had to reshape our tabular embeddings into 2D map, which is quite counterintuitive because it's difficult to imagine the 2D representation of tabular data. But as we've seen in our experiments, the addition of spatial attention module was also giving some performance gain. Therefore, we have decided to stick to it. And finally, we also had the temporal attention module. In this module, we are following the same approach. So we are having max pooling and average pooling vectors, which we could pass through dimension-specific layer, in which we have decided to use multi-head self-attention layer for temporal information processing. And then, of course, we added tabular embeddings, which were of the same size as max and average pooling vectors. Finally, we could integrate tab attention within residual block and apply tabular data in ResNet architecture. So when it comes to mathematical formulas, the simplified mathematical formulas, you can see that what I also told you earlier, that we only follow max and average pooling with the addition of tabular embeddings. And here, when it comes to the results of our tab attention, there are now BabyNet++ results because they weren't published at the time of developing the paper, but BabyNet++ was receiving slightly worse results than our tab attention module. And here you can see the interesting thing that the simpler tabular methods are achieving better results than vision networks, which gives us, again, the emphasis on the fact that we should take the advantage of all the available data that we have for the training. And finally, when it comes to the ablation study of the tab attention, the integration of especially temporal attention module, as I told you earlier, was quite important because we could find the most important module for, we could find the most important frame for the analysis of fetal ultrasound videos. So when it comes to conclusions of this paper, we have introduced a new module that was enabling the conditional learning of attention on tabular data. And there are multiple other potential applications that we have, because, as I said earlier, many clinical workflows include the combination of imaging and tabular data. And that's why we are moving to slightly different clinical topic, which is now the main clinical topic of my PhD, which is pulmonary hypertension diagnosis. Because we somehow created the closed solutions when it comes to fetal birth weight prediction. Of course, there is a lot of work still to be done, but I also wanted to move on with the collaboration with the University of Sheffield, which focuses on the pulmonary hypertension diagnosis. So let's talk about our heart. Our heart functions as a pump, facilitating the distribution of oxygenated blood throughout our bodies via systemic circuit. The problem arises when the pressure within this circuit becomes elevated, but we can easily measure this pressure via blood pressure monitor and find out whether we are suffering from the arterial hypertension. And it turns out that there is a second circuit in our circuit, which is called pulmonary circuit. And this circuit's goal is to oxygenate our blood. And similarly, the issue arises when the pressure within the circuit becomes elevated. And unfortunately, the problem is that we can't measure this pressure so easily, and the go-to standard for measuring the pressure is invasive and required for diagnosing pulmonary hypertension. This procedure is called right heart catheterization and involves inserting catheter through one of the insertion sites. Then the catheter navigates through right atrium and right ventricle to reach the main pulmonary artery, facilitating the measurement of mean pulmonary artery pressure. The problem with right heart catheterization is that it's invasive, and as an invasive procedure, it has multiple risks, is costly, time-consuming, and requires specialized staff, equipment, and facility. So in this context, the development of non-invasive techniques for pulmonary hypertension diagnosis could revolutionize the field, significantly impacting the patients' lives. I am the principal investigator of the project funded by National Science Center, which with the title Multimodal Deep Learning for Non-Invasive Pulmonary Hypertension Diagnosis from Magnetic Resonance Imaging. And in this project, the goal is to use cardiac magnetic resonance imaging combined with tabular data to replace invasive right heart catheterization with multimodal deep learning, combining imaging data and tabular data for the mean pulmonary artery pressure estimation. And within this project, I also worked on developing new models, new modules, and methods for combining imaging and tabular data. And this led to our newest MICCAI publication, which was early accepted last month, which is called TabMixer. And TabMixer is another module which enables non-invasive estimation of the mean pulmonary artery pressure via imaging and tabular data. So what were the related works? As I said earlier, when it comes to deep learning, the go-to standard for tabular data processing are and were, of course, multi-layer perceptrons. But then in 2021, it turned out that we could also use multi-layer perceptrons if we use some specific tricks to use multi-layer perceptron in vision tasks, in image processing approaches. The idea of MLP mixer is that we are splitting image into non-overlapping patches, which are being embedded via simple fully connected layer, and then they are passed through multiple mixer layers in which two mixing operations are happening. First of all, the patches mixing, so the information across patches is being exchanged, and second of all, channel mixing. So the information within patch is being mixed. And while those models haven't achieved the state-of-the-art results, they were on par or slightly worse than the newest vision transformers or convolutional-based architecture, which gave some kind of interesting outlook on how we can circle back to simple multi-layer perceptron when it comes to vision tasks. And following MLP mixer, multiple other architectures appeared like ResMLP, GMLP, CycleMLP, but all of those solutions were based on the same idea of using multi-layer perceptrons for exchanging information between patches and channels. And basing on those ideas, basing on those approaches, we have decided to try out whether we could use MLPs to fuse, to mix tabular information, tabular data with temporal feature maps. Now we weren't analyzing ultrasound feature maps, but we were analyzing cardiac MRI feature maps. So how we approach the problem? The idea is quite simple, but works very well, which was quite exciting for us. So first of all, if we have tabular data, we can create tabular embeddings. As always, we are using simple, fully connected networks, multi-layer perceptrons to embed tabular data into a vector of specific length. Then we have decided we have to find out the way to mix the information from temporal feature maps with information from tabular data. And the idea was to concatenate tabular data over a specific dimension over which we are going to compute the mixing methodology. So we were computing the mixing operation over spatial dimension, over temporal dimension, and over channel dimension, which led to finally refined temporal feature maps, which consisted of the information appearing in imaging data, but also the tabular information was mixed within. And we tested Tab Mixer with multiple vision architectures in which the vision backbone was based on transformers, on convolutions, or even MLPs. And in all of them, the Tab Mixer, the introduction of Tab Mixer and tabular data was decreasing the prediction error, which is quite important for us. And second of all, in most of the cases, we were receiving the lowest error in comparison to all other tested modules, as well as our tab attention. And when it comes to the ablation study, we also tested the importance of channel mixing, spatial mixing, temporal mixing, and it turned out that all of those modules were important. So finally, when it comes to conclusions of this paper, we have introduced new module facilitating the integration of imaging and tabular data in hierarchical vision models. And to our knowledge, this represents the first application of MLPs with the idea of combining those two modalities. And while the prediction error wasn't as good as we wanted to be for the clinical introduction of those solutions, it holds the considerable promise when it comes to non-invasive MPAP estimation. And with this paper, we are finishing the idea of combining imaging and tabular data. But I would like to tell you about one more paper that we had, which was focused on utilization only tabular data, but from slightly different perspective than traditional methods do. So I would like to present also the MIS multi-class interpretable scoring systems, because the previous solutions that I was showing to you have problems with the interpretability. This is the biggest issue of deep learning models. We have problems with explaining the predictions, interpreting them. So my goal was to slightly shift towards interpretable methods. And then my final research goal during my PhD is to find out whether there would be a possibility to combine the interpretable scoring systems with vision architectures. And for that, I had to work on interpretable scoring systems, but also had to work on the integration of imaging and tabular data. But let's start with scoring systems. Scoring systems are quite widely used in domains where conscious and fair decision-making is vital. Therefore, they are quite popular in medicine, in criminal justice, and the idea of them is very, very straightforward. So given the binary features, we are having assigned points to every binary feature. So then if we have exemplary sample with binary features, we can check which points are being positive. And then based on the positive features, we are summing all of the points, which we can later interpret from the score interpretation table, or we can use some function to compute final risk score. For example, QSOFA score computes the risk of in-hospital mortality, but we also have CHATS2, which gives us the risk of ischemic stroke. And due to the fact that those models are very simple, they are quite powerful. Of course, maybe their performance is not exactly matched up with some huge deep learning models, but they are not that poor. They are quite efficient, quite good when it comes to prediction errors and accuracy and all of the others, the other classification metrics. Therefore, clinicians love to use them. And how do we build them? There are a couple of methods for building scoring systems, and the simplest one consists of training logistic regression and then rounding on and/or rescaling weights of the logistic regression. The simpler method consists of unit weighting, so we are assigning plus or minus 1 points depending on the weight and the sign of the logistic regression weights. And finally, the quite important method which we based our solution on is based on integer programming and is called RiskSlim. The motivation for our work is that real-life decision-making processes often require a multi-class analysis. And when it comes to scoring systems which were available for us, they were only binary. So there was no straightforward solution on how to train multi-class scoring systems. The existing ideas, possibilities were, for example, to train one versus rest scoring systems, which would give us the scoring system for every class that we had. For example, if we had 3 classes, then we would have 3 scoring systems. The problem here is that we have different features in every scoring system, we have different points and different functions for computing probabilities. This led to our idea of introducing MIS, multi-class interpretable scoring systems, in which we are using the same binary features for all classes, but we are assigning different points to every class depending on the binary feature and whether this binary feature impacts the class negatively or positively. So, for example, given some features, we can find which binary conditions are being met. We can sum points for each of the classes that we have. And by taking the highest score, we can find the classification results of our methods. If you wanted to achieve the probability of our scores, we could compute the simple softmax method. And I don't want to bore you with equations, and also due to the fact that we are reaching the end of my presentation, the time for my presentation, I just wanted to give you a short information on how did we train those MIS models. So we used the mixed integer nonlinear programs in which we were minimizing the softmax cross entropy loss. The idea of solving this mixed integer nonlinear program was to solve multiple surrogate linear programs in which we could create some constraints, the size of the model, the possible coefficient values, the numbers of features used, and then by optimizing the softmax cross entropy loss, we would achieve our resulting multi-class scoring systems. And here you can see the examples of scoring systems that we managed to create. One of the interesting things is at the top, you can see that MIS can also work for binary problems. So we can have, instead of having only one column of points, we can have 2 columns in which we can have more interpretability when it comes to impact of each of the binary features on the final classification. And at the bottom, you can see examples of MIS models when it comes to 3-class classification problems. There are, of course, limitations to our methods. method. First of all, the solution to integer programming based program is quite computationally high. There is lots of computations that are being made, and especially if the data set is bigger, we have more features, then we come to problems that the optimization computation takes quite a lot of time, and the performance highly depends on the binarization procedure when it comes to binarizing features that are, for example, categorical or real valued. When it comes to the conclusion of this paper, we introduced new IP-based method for the creation of multi-class scoring systems, which works also for binary tasks. And the great thing about those models is that they are characterized by their simplicity, ease of use. We can remember them quite easily. They are quite scarce and quite much interpretable. And that's the end when it comes to all of my papers. So the general conclusions of my presentation would be that there are quite many, if not all, clinical procedures that involve collecting imaging and tabular data. So efficient utilization of both modalities is important for improving non-invasive diagnostics, for improving our decision-making processes. And as I said earlier, my future research will focus on developing models which can handle only imaging and or tabular data, but would also provide maybe some interpretable scoring systems. I have the ideas for that, but I'm not sure whether they are going to work. So I think that this is the topic for my future presentation. And with this, I'm going to finish my presentation, and I'm open for any questions that you might have. Thank you very much.
Well, many thanks, Michał, for your talk and giving overview of your current of research up to now. Well, now as we have agreed and we have as usual, there is a time for questions, for discussion, for remarks related to your work. Well, during the talk there was no question on chat, so I hope that it will be now. Jose, well, go on, please.
Yes, can you hear me?
Yes.
Yes, we can.
Okay, perfect. So very nice and interesting presentation, Michał. Congratulations on that. I just have two questions. One is you use this feature level fusion, okay? If I understood well.
Yes.
Did you consider to look into the other approach that could be like decision level fusion, that could be a little bit more similar to what the decision process looks like? For example, that you take a prognosis from images, and then you go and you look into additionally on the features that come from clinical data, and then you get an additional informed decision. So instead of combining the features and then putting those features under a deep learning model, that then would be difficult to explain, and then gives you additional problems on the explanation process. The second thing is that when you describe your last work, the MIS, you use a transformation so you binarize the data, okay? We are quite interested in that because we do a similar thing, but because we do data abstractions, for example, using ROC curve based on the distribution of the data, we get up and downs. So it's good to see that you are considering that as a way to deal with explaining the data, so explaining the decision-making process, because we are able to explain on our models using those simple transitions. So.
Okay, so coming back to your first question, first of all, thank you for those questions, and both points being made are extremely valid. We haven't investigated the fusion based on decision level. I think it's due to the fact that there comes the problem of having two decisions coming from two different modalities, and then we are limiting the interaction between those modalities. So we can have, of course, that from images we are receiving this prediction, and from tabular data we are receiving this prediction, but then the models that we are training do not have the possibility to for those modalities to interact with each other. Therefore, we focused more on this approach. And also there might be problem of interpreting how, for example, if one method predicts 90% and the other one 40%, why at the end we are receiving 60% or 80%. But of course, I agree that this type of approach is also interesting for checking out. We haven't worked on that in our works.
Yeah, but that's where it could be interesting. For example, you mentioned the theory of attention, and the attention. So it's always, so you can build, for example, on attention theory to understand what is the level of confidence that you have in a certain model and a certain outcome. Because not only, so you don't always have imaging and data, or if you have them, you'll have in different stages of the diagnosis process. I don't know. So just a couple of ideas that I'm just putting forward.
Yeah, I think that maybe the best way would be to do both. So first of all, you can interact between different modalities, but mainly the decision is based on images or tabular data, and then you can finally combine the final decisions or predictions made by the models. And when it comes to your second question, it's extremely valid as well. And this is huge limitation for the scoring systems that we are working on. The approach that we used was developed by Arek Pajor, who was a master's student 2 years ago at Sano. And the idea was to create multiple training processes in which different binarization strategies would be used. And then at the end, the best model would be chosen. But that's, especially when we have a long time of training, that is not feasible and quite complex. So we try to find ways maybe to inject binarization procedure within the optimization problem. So that was one of the ideas. But then again, the complexity might rise again. So we've seen that there were some slightly different approach this year at NeurIPS when it comes to learning scoring systems without integer-based programming approaches. So probably those integer-based programming approaches are too slow to create some really feasible models and training strategies.
Mm-hmm.
Thank you, Michael, for the explanation. Thank you.
Many thanks, Joseph, for your question. Well, I'm looking for more questions. Well, in the meantime, I would like to ask you about, you have in your talk few times used complexity. What do you understand by this complexity? It is just simply something which is not polynomial, or it is just amount of time, memory, complexity of solving these linear and not linear programming problems?
Yes, so in this case, I know that I've been using complexity in quite vague way, and that's good point. So when it comes to mixed integer nonlinear program, it's about NP-hard solutions and problems that we have to solve. But when it comes to deep learning, I was using complexity as a general term for memory restrictions, time for training, and number of parameters that the model has.
I understand. So it is really something important. Well, we have there is a question on chat. Not one, there are more questions on chat. So maybe let's try to. What do you think? The first question is, what do you think about clip pre-training model? Have you made any comparison clip with your model with Fafetal birthday prediction? So this is the first question.
Yes, so we haven't made that comparison because first of all, clip was trained only on images and we were analyzing videos. I know that there is a clip for clip, so a model with quite a funny name for analyzing videos. But the second thing is that clip model was trained on natural images mainly. It would be good to pre-train clip on some medical data, and then we could try to use it for fetal birth weight prediction. That's one of the good ideas to follow, because the self-supervised pre-training shows a huge performance gain in natural data. So for medical data, I'm sure there are approaches based on that already as well.
Guo, would you like to add something to your question? Well, I think that maybe we'll have Guo on chat more, and I have on chat another question, which is from Jean. Well, it is a question is about training procedures. Do you train all of the weights at the same time? Frozen weights, transfer learning?
So that's another good question. So we are training our model, all the weights of our models, and it's quite good idea to consider, for example, if we had only imaging data, we can train the model, and then we can add new modules, and then only train the weights of those modules to transform the imaging data, and that would take less time than retraining whole model. And when it comes to transfer learning, some of the models that we used had the pre-trained weights, but some of them didn't have the pre-trained weights, of course, on ImageNet, which slightly improved training on medical data, but not that much. So there we haven't seen that much of a difference when it comes to having pre-trained network or not.
Okay. Okay. Well, Jean reacted. Interesting. Thanks. So now we have in the queue we have Tomasz Szczepański. Tomasz, please go on with your question. I hope there will be no obstacle to ask this question.
Hi, can you hear me?
Yes.
Yes.
Okay, thank you, Michał, for great presentation. Your research questions are very interesting, and I have also one question to you. How do you think? What is your intuition about generalization of models that use mixing different modalities? Whether the additional tabular data that you work with, do these types of data make the models more robust? for domain adaptation or generalization of those models on new unseen data? And do you think that the risk of memorization of the data sets, so-called overfitting, is the same when we combine different modalities? Is it stronger or weaker? What are your experiences and your intuitions? Thank you.
That's another very good question. So in case of training tab mixer, we were working on the dataset from the University of Sheffield, which contained around 3,000 videos, which is much more than when it comes to our fetal ultrasound videos dataset, which is better for our generalization problems. But still, it isn't that much when it comes to deep learning. So I would say that the addition, we haven't tested that because we didn't have access to to a dataset from other institutions to check the generalization error. We are collaborating with Arkadiusz Sitek and Massachusetts General Hospital, which I'm going to visit, and we are going to have access to bigger dataset from other institutions. And this would be a good point for checking whether the addition of new modalities improves the generalization, or maybe, as you say, there is a stronger overfitting. My intuition is that the additional modality might give us another information, another point of view on the decision-making process. So it might be easier for the network to find the solution for the problem. But of course, this solution might be the shortest path. So I think there is always this issue of generalization error, and we have to investigate it, because without checking on some other data sets, we can't really say how big is it.
Okay, thank you. So that's great that you have opportunity to assess this on larger data sets. It would be very interesting.
Well, and thank you. And now we'll have questions from Wiesław Nowinski. Wiesław, please go on.
Yeah, thank you, Marian. Maybe I start from a comment. It's really a nice topic. And a few years ago, I tried to combine tabular data with imaging data in the aspect of stroke or stroke prediction. And the idea was, it was non-AI based. The idea was that we converted stroke scales into images and then used those images for interpretation and prediction. Yeah, this work was published in +1. But my first question is, congrats for your Michał papers. These are oral or poster presentations?
Michał 2022 and 3 were posters, and we are waiting for final results of Michał 2024, and we'll see. Maybe we'll get oral presentation this year.
Okay. Yeah, in your first project about BabyNet, at the beginning you mentioned that you have done some pre-processing of US images, noise, and so on. But a quick checking shows that on Google Scholar there are more than 500,000 papers about this topic. How you are different?
You mean about the topic of fetal birth weight estimation?
No, about processing, pre-processing, enhancing of ultrasonic images. Maybe
Okay.
different contexts, but anyway, it's something which usually when we do research and publish, we need to take care of state of the art.
Yeah, so we, in our work, we made some standard pre-processing steps which are being done in medical image processing. We haven't focused that much on enhancing the ultrasound videos or denoising them. We haven't used those approaches in our works.
Yeah, and my question is quite naive because you see, when you try to estimate the baby weight, you use some geometry, yeah, the size of head and so on and so on. But why don't you try to estimate how much is soft tissue, how much is bone, how much is water? So the underlying tissue is not in the picture?
I would say it would be difficult for us to create a data set for us from the data that we had. It would be, it's quite a good idea to do this. I think it's way better because we have more interpretability if we can predict how much tissue, fat tissue, for example, we have, and so on and so on. But we couldn't directly apply our data set to this kind of tasks. So that's why we focused on the measurement that we had, so the weight of the baby obtained post-delivery.
But as I understand what you are saying, this information is in the data, but you basically don't take it into account? Or...
So we hope that the deep learning model during the optimization process will find the most important features related with the estimation target, prediction target, and find out the most important features on its own. But as Tomek mentioned, this might lead to generalization errors and memorizing data sets. And that's why it's quite important to investigate what the models, which features are models using for their prediction. But this is the problem of the whole deep learning community right now.
It's the next project about pulmonary hypertension. You mentioned MRI somewhere, but you didn't show any images. What sort of imaging and how do you visualize the heart?
So those were 2D videos of short axis and 4-chamber cardiac MRIs. I think I have one slide which shows, I can go back to it. It would be easier to explain. Oh, here we have those 2 views which we were analyzing. And we were comparing which view, which I haven't mentioned in this paper. We were also comparing which view was giving us the best results, because we haven't focused yet. That's one of my future goals as well. We haven't investigated the fusion of those views, but we only used one of those views. So we used 4-chamber or short axis view, and it turned out as expected by our clinicians that short axis view led to lower error and better predictions because it contains more important.
What you are getting from this view? What sort of information you are extracting?
So from this view, we can see the sizes of ventricles. We can see the different angles, for example, septal angles that are being computed on the video. And we are also extracting the information that maybe isn't used by clinicians right now, but maybe the deep learning model finds some other features that are important for the prediction target. So
if you examine the beating heart, why don't you use TEG MRI? Which gives more information about dynamics. It's first of all because in our collaborators from the University of Sheffield focus on this type of MRIs in their research, and that's their research path to find out whether from cardiac MRIs we can investigate and diagnose pulmonary hypertension, and that's the data set that
I have available for my research.
So perhaps your visit to Marzhen can help you to explore this topic, to have a better data to be more clinically relevant, just a suggestion. Do you have any publications or plan any publications in clinical journals?
Not yet, but we plan to have one regarding this non-invasive estimation of new pulmonary artery pressure, but it's still work in progress, so I don't have that much information about that.
Okay, so good luck. Thank you.
Many thanks, Wiesław. Now we have Go on ready to ask question. So go on, please.
Hi, can you hear me?
Yes.
Yes.
Okay. I don't know if my camera is working or not, but I just want to thank you for answering my first question. My second question is about the fetal birth weight prediction. So you use the ultrasound scans. I'm wondering, have you done any pre-processing of the images? For example, have you done any filtering work on the scan or videos or any other sort of pre-processing?
So we haven't done that much of a processing. So we focused on removing the patient information, which was appearing at the top, so we could easily crop out the information about the patient from the ultrasound video. But apart from that, we were following traditional image processing approaches like rescaling the image, cutting, cropping into 16 frame segments, and so on and so on. But we haven't applied ultrasound specific processing to our data.
You didn't choose specific area of interest, such as the head or the femur or something like that.
Yes. So our idea from the beginning was to create a method that would be able to analyze whole ultrasound videos. And because right now what's being done is that clinicians are recording videos and they are finding the most important frames from which they can conduct the fetal biometry. But then when it comes to the video that is being recorded, it can contain information in all of the frames, but most often it isn't like that. So we wanted to process whole videos with our networks, and we created a very simple approach of averaging the predictions from 16 frame segments from the video.
Okay, thank you very much. Thank you. Great.
Thank you.
Thank you. And Jose, well, you are once again with your question. Go on, please.
Yes, so just a follow-up, Michael. You mentioned that when you tried deep learning, the feature stability was not very good. So that would make difficult to explain, what the outcomes that you are getting. So I just would like to let you know that we are going to publish a paper where we demonstrate that our methodology, up to 20% of missing data, gives more stable features, or presents the stability of feature that is not present in any traditional machine learning approach like XBoost and that sort of thing. So one of these days, if you are at Sano and you want to have a talk about how we do it, so I'll be more than keen to tell you if that can help the things that you are trying to approach.
Perfect. Thank you.
Thank you very much. It seems that we do not have more questions, suggestions, and so on. But anyhow, we are almost reaching the time assigned to this seminar. So many thanks to Michał, and many thanks for all who decided to take part in the discussion. Thank you very much. And I would like to invite all of you to next seminar of this series in a week from now. The speaker will be Rosemary Blanco. It will be on Monday, June 17. Thank you very much and see you in a week.
Thank you very much.
Thank you. Bye.